to get back to it, now we've looked at in depth, we've looked at the oscillators mini app. We've looked at the lamps demo. So let's get back into this and go through some other demos. You know something? It just occurred to me that we never ran the oscillators mini app. If we have time, we'll go back to that one. So now let's talk about using VisIt and specifically data extracts. So data extracts are where you're going to do some kind of subsetting or feature detection, and then write out that reduced data set. VisIt, Libsim, Catalyst, these tools can do this. For instance, you subset the volume based on some criteria. You could use a threshold. You could compute an isosurface, take a slice, and write that out. So you're writing a part of the data out, just the relevant part that's relevant for you. And the advantage of doing this versus rendering is that you can actually fine-tune your rendering and analysis after the fact. You're reducing the amount of data, so you get a higher temporal resolution. Hopefully you get more relevant data this way. But it's much smaller, so you're really focusing on getting the most use out of the resources that you have available in terms of I/O. Okay, so Libsim puts VisIt in situ. We've talked a lot about Libsim. It's the part of VisIt that lets a simulation do in situ analysis. You can use it to reduce your I/O, do stuff automatically as a simulation runs, or interactive live exploration by connecting to the VisIt GUI. It's open source. Enables a number of different use case scenarios, as we just mentioned, interactive exploration with the GUI. VisIt has this beautiful abstraction called the database. So all data sources in VisIt use this database abstraction, and Libsim, in fact, uses that as well. So at a low level, Libsim, you need to provide callbacks to Libsim. And these callbacks are invoked by VisIt's database abstraction. So in this way, simulations appear to VisIt like any other data source. So anything you can do in the VisIt GUI by opening a file, you can also do with Libsim in your simulation. In addition to that, though, you can do these automated batch runs. You can use VisIt session files. So you would open a representative data set up in VisIt, record a session file. A session file is like an XML file that captures the state of the GUI. Then at runtime, you can use this session file to initialize Libsim, set up your rendering pipelines, and configure it to write files out, extracts or renderings. And there's yet another way of using Libsim through Python scripts, although it's a little bit more tricky. We want to see that become a first-class citizen because it's very powerful for in situ. XDB workflow. So XDB is a file format used by this other rendering tool called FieldView. So FieldView is a commercial data analysis tool. It's a serial tool, so it's meant for desktop use. However, in past few years, the company Intelligent Light that designed and creates FieldView and sells it actually hired Brad Whitlock, who's a VisIt developer for many years, to parallelize FieldView, and they're actually using VisIt behind the scenes in FieldView to render stuff. So that's, when we talk about FieldView, that's kind of some of the context and the history. And XDB is one of these file formats that's very popular by FieldView users. It's basically a CFD domain-specific format. designed for streamlines and surfaces. So the whole idea with extracts is that they're orders of magnitude smaller than the simulation volume. So you're avoiding this I/O bottleneck. And XDBs are easily consumed by this product called FieldView. And it ends up being a lot faster in terms of your rendering and your analysis because the XDBs are much smaller than the full simulation set. So basically the workflow is you run your simulation with Libsim and dump out these XDB files, open them up in FieldView after the fact, and you do your analysis on the reduced data. And the great thing is that you don't need to set up all these rendering pipelines. You don't need to fine-tune your rendering, which is very difficult to do, I'm sorry. And this permits interactive exploration after the fact. And the reduced amount of data that you end up writing out makes it possible to have these very high temporal resolutions. So flexible extract export. So the way that you can configure Libsim in SENSEI is through this XML file. And let's see, here's a Libsim analysis. The operation is export. The plots are pseudocolor. The plot variables are going to be P, rho, T, YO, Y, H2O, vorticity. The file names are going to be specified here. There's going to be a slice, and he's providing the parameters for the slice. These kind of things are kind of built into our XML parser, and it configures from them. So if you're rendering, the important one is the plots, and you use the name of the plot that VisIt uses, and it will add these into the rendering pipeline for you. Jean showed yesterday how you could use the Python tracing feature in VisIt. I'd really like to see in the very near future Libsim via SENSEI support a Python configuration similar to how we do it with Catalyst. So that's something I'm going to work on, but for the time being, we're doing this for rendering. So we add plots this way, and we use the plot vars to tell what variable we're going to plot. And for exporting, which means writing data to disk, we're using this operation export kind of keyword and the file name to say where it's going to be written. Okay, so that's the XML that is used to configure Libsim at runtime in SENSEI. So AVF-LESLIE is a CFD solver. So to use it with SENSEI, what Brad's done is he's created a data adapter. From the AVF-LESLIE simulation, he's calling compute when he wants to generate Libsim extracts. So this is the bridge code. He'll be calling compute every time he wants to create one of these. And he's going to use the Libsim analysis adapter that comes with SENSEI to push the data through to Libsim. And then in there, he's using the XML to configure it to dump out in the XDB format. So here's a nice block diagram of how everything works. We've got AVF-LESLIE simulation. We've got our bridge code with the initialize, compute, and finalize. And we've got our data adapter, or our adapter library, which got Libsim in it, the VisIt runtime, doing the XDB dumping, and the callbacks. Adapter callbacks are the hooks into Libsim in the Libsim analysis adapter, with SENSEI in between all of this. And SENSEI, of course, gets the XML file. So as this simulation runs, AVF-LESLIE, he's using 0 copy, sending pointers over through the compute. Data gets pushed through SENSEI, through Libsim, and eventually goes down to disk as XDBs. After the fact, he's gone and done these beautiful renderings. And those actually appeared on like the website of Supercomputing, I think in 2016, just like everywhere, those images were shown. So this is about the performance of the in situ extract generation and a little bit about AVF-LESLIE. So he's running it as a combustion turbulent mixing use case. He's going to save vorticity isosurface every 5th iteration for rendering in the field view, but he's dumping out isosurfaces in this XDB format. He's set up this writer group thing to aggregate data to reduce the number of writers. So let's look at these charts that he's done. These are benchmarks that he's run. So while he's running this, he's doing in situ, he's computing the solutions, right? And he's also dumping the whole solution. So he's doing everything. He's doing the old way of dumping out the whole solution. He's doing the extracts while he computes. And so on the x-axis, we've got the number of cores that he was running at, and the y-axis is the time. And then the breakdown of this is that the orange is the dumping of the entire solution for that time step. The yellow is the dumping of the extracts, and he said he has generated 20 extracts, so possibly 20 isosurfaces per dump. And this is the compute time of 100 solver iterations. So the in situ times are a lot less than the actual file writes to dumping the whole solution. So it's a huge savings. So I'm not actually sure what his numbers mean here, but you can see just from the plots themselves that the yellow band is a very small slice compared to the orange band, and that's the point that extracts here are saving a lot of time. So the in situ is a huge win over the post-processing I/O scenario.
Sorry, and the mesh size is the same everywhere? It's like strong scale?
That's a good question. I'd have to ask Brad. I'm not positive. I think it may be actually, I'm guessing it's weak scaling, because if it was strong scaling, you would expect to see some kind of speed up.
The green part is exactly like 2 times less.
Possibly. Let's save that one for Brad, since he knows more about the details. Yeah, it'd be interesting to know. The green part does seem to go down. The orange part seems to go up. The in situ costs, I mean, these heights, I mean, there are variabilities, between runs as well. So I don't know. It's hard to say. And this scale is actually, I don't know. It covers a lot of. It's not very fine scale. It's hard to see with the eye. So the conclusion, though, is that between 1/30th and 1/50th of the cost of full I/O, you get a 10x better temporal sampling with the extracts. And we have information about Libsim here. VisIt has extremely good documentation. This documentation has a lot of information about VTK mesh types as well. It's really good. It's well written and easy to follow, and it has examples. There are example simulations that come with VisIt, and actually the Jean's P. Jacobi example is in there as well. Finally, visitusers.org has a wiki with a lot of developer info, and there's an email list where you can ask for help. So with that, we'll take a quick look at this live demo. Switch over to the VM, and I suggest that you guys try this as well. Start up a terminal here. Make the font size a tad bigger. Okay. SC17 demos. VisIt Libsim. Let's look at what's in here. Okay, some data. You know what? I'll hit Brad up and ask him where the source code lives for this. I'm not totally sure where the source code for the data adapters is, but in terms of the demo, there's demo.sh, and this script is a shell script that does all of the heavy lifting of the demo, and so it's very nicely written. There's a menu. There are different stages. So in his slide, Brad's recommending that we go through and run 0, 1, 2, 3, 4. So let's take a quick look at doing that. So the demo.0, that dumps out the XML file that configures the analysis adapters. This is how Libsim is configured. So he's doing extracts. He's got this operation export, frequency 5. So it says every 5 steps, he's going to dump out all of these variables on this slice plane in this demo. And let's see, it's enabled, so that's going to run. He's got another one. He's got another slice plane. The difference here is the normal. So this plane is normal in the y direction. This plane is normal in the z direction. He's got yet another one. And let's see, this is another slice plane, normal in the z direction, project. He's projecting it down, though, into probably xy plane, and he's writing it out as an image. So this is a rendering example. So this is render versus export. Okay, so now let's run the demo 1. Okay, older results removed. I guess he was cleaning up the old results. Demo 2. Now this is starting the solver. And so this thing is cranking away. The solver is computing something. While that's going on, I'm going to open up another terminal and just do a little bit of exploration into the shell scripts to see what's going on. So that was demo 2. He's doing an MPI run of the simulation with 4 processors. So we're going to have to wait for that to finish. Once that finishes, the next action that it's going to make these .visit files. So .visit files is a metadata file for VisIt. It's like a text file where you can tell VisIt about the files in a data set. So it treats a set of files as a single data set. And you can pass info like the extents and the time. So he's making a .visit file. And then he's going to launch VisIt and use a session file to start it up. So he's saved this rendering configuration in a session file, and it's called demo.session. So session file, again, is something when you open up a data set in VisIt, do some visualizations. You can then, with the visualizations active in the GUI, you can save a session file that captures the state of the GUI, then reload that session file later, and it will restore that state. So it's a good way to, let's say, go have lunch. You'll save your session file, shut everything down, go have lunch. You'll come back after lunch, use that session file to restore the GUI. And let's see. Okay. So here's what the session file looks like. This is all XML generated by VisIt when you save it out. This type of thing can be used to configure Libsim as well. So in that case, instead of saying the plot names in the XML file for SENSEI, you would pass in the path to the session file and use the session file. So the simulation's still running. We can see it cranking away. It's going to take, I don't know, a little bit of time here, but it should be done soon. In the meantime, I'm going to just take a quick look for his source code. Okay, so the simulation is done now. It's dumped out a bunch of data, which we can see these .dat files. Okay, so we'll go back, we'll run the demo step 3, and that's going to create a .visit file. So let's see if we can see this thing. In here. Not actually sure where it put that, but it's in there. So I'm going to run the 4th step of the demo. This is launching VisIt with using the session file, the XML. And now we're interactive in VisIt looking at the simulation results. So the extracts that Brad had wrote are these slices. And so we can see the slice planes now. We can tune the rendering parameters. He's got these plots defined. We're fully interactive. We can do different things. We can change, I don't know, the lookup tables like that. We can do anything now. We've got the data. This is all set for visualization post-processing. And we've got the time axes here. We can change time steps. And I will, after the fact, I'll ask Brad where his adapters are, so that, see if we can get those to you guys for examples. Although, one thing is that AVF-LESLIE, it may be a commercial code, so I'm not sure what the rules are about sharing that. That may be why they're not in there. Okay, so that was the AVF-LESLIE demo. With extracts. So computational monitoring and steering with ParaView Catalyst. So in this demo, we're going to connect up to the oscillators mini app, and we're going to use the mini app just to generate some data and connect over with Catalyst Live and show some of the features of Catalyst Live. So Catalyst Live is the way that you take ParaView and connect it to a running simulation and interact with the simulation as it's running. A little bit of background about Catalyst. We've covered some of this. You could either do batch or interactive through Catalyst. To get in transit, you've got to use some other layer. If you do write an ADIOS writer and an ADIOS reader, you could use that ADIOS reader inside of a ParaView plugin to stream data in transit. Or SENSEI can do that for you. Catalyst used Python scripts to control the visualization. There's a tool called Cinema that comes with Catalyst, which we didn't talk much about, but what Cinema does is it renders images from inside of a camera-like sphere. It moves the camera around the sphere, and it renders all of these images. And then, so after the fact, there's a special application called Cinema that can take all of those renderings and reconstruct like a three-dimensional view from these renderings. And you can actually interact with the data. It looks as if you are interacting with a real data set, although it's just a set of images. So it's a pretty neat technology. Oh, cool.
Come to the movie tomorrow.
So Catalyst supports Fortran, C++, and Python. Some of the notable achievements with Catalyst have been, running 1 million MPI ranks on Mira BGQ. This was with a CFD application, an aerodynamics code called Pasta that the scientist was using to design a better wing. He was looking at boundary layer separation and turbulence on these wing designs. In SC16, the SE visualization showcase winner used Catalyst. It has a number of awards bestowed upon it. It's a great thing. It has this computational monitoring capability called Catalyst Live. It allows the ParaView server to connect over to a running simulation. This can be done remotely on PitsDaint or wherever your simulation's running. Your GUI is gonna run on your desktop or your laptop. You can ship the data from the simulation over to ParaView for visualization. You can connect, disconnect, running multiple times to the simulation. So this gives you a way to kind of check in on your simulation. You can set up your Catalyst Python script to dump out images or extracts But then as your simulation runs, it may run for like 10 hours or something. You can periodically go in and connect with this live feature and see what's actually going on, make sure everything's going well, and disconnect, and it won't interfere with the simulation. So this is the type of XML that we use to configure Catalyst and SENSEI. So we've got this element, we say type Catalyst, pipeline equals Python script, and the file name. That's the XML. The Catalyst Python script on the far right does all the configuration of Catalyst. The in situ architecture here, we've got, or for this demo, we've got the oscillator mini app. It's got its own data adapter and bridge code. We're going to tell the oscillator mini app to create this Catalyst analysis adapter and give it this XML file. It's going to take that and do the rest. And so this shows how the Catalyst Live works with this. You've got your in situ job running on the left. It's all set up, it's running, it's cranking away, solving, dumping out stuff, rendering or computing extracts. Then Catalyst Live comes along, you start up a ParaView GUI. We're going to walk through how you do this, but you connect over, you tell the GUI to connect over to the sim, and then all of a sudden the simulation pauses and you're looking at the simulation data in the GUI. So all of this stuff runs over, on your HPC center. This is a machine at Argonne, the ALCF, and this GUI is running locally on your workstation or your laptop while you're doing this. So here's the demo. We'll go back into the VM, and we'll take a quick look at this. There are these scripts again in the VM, so we can launch the thing with this script, and it will do everything for us. And then we can use these menus up here, the Catalyst menu. We can connect. We'll use the default port number, hit OK. This thing will connect back to the server. Then we can do different things like pause the simulation, continue, set a breakpoint, remove a breakpoint, and we'll walk through those things. When you're using Catalyst in this live mode, once you connect, you see all of the pipelines that Catalyst is using. So this is the Catalyst server. The input is coming from the simulation, and then these are your visualization pipelines. This is a cell to point data. This is a VTK filter that converts cell data onto nodes. Contouring is an isosurface. And then he's got a writer for that. So he's writing out an extract. Here he's writing out the raw data set. And then finally, he's taking a slice and writing that out. So he's generating 3 extracts, and he's got these pipelines set up. So when you're in Catalyst and you're live and you make this connection, there are these icons. When they're grayed out like this, that means the data is over on the simulation. Nothing's happening with it inside of ParaView. When you click on it and make it blue like this, that brings it over to the server and sets it up to be rendered. And then you have to click on the eye to make it visible in the GUI. And it says use delete to tell it not to transfer that data anymore. While you're running, if you're doing the breakpoints, starting, stopping, all of this is visible. You can tell the simulation state through this icon right here. If it looks like this, the simulation is paused. If it looks like this, the simulation is running. If it looks like this, it means there's a breakpoint set. And when that thing disappears, the breakpoint will be hit. So at this point, I want to switch back to the VM. And I'm going to suggest that you also do that, and so you can try this demo out. So again, I'm going to increase the font size a little bit. Okay. So in this ParaView Catalyst folder, there are two scripts in here, run_simulation.sh and clean.sh. I'm just going to run the clean.sh. That's going to clean up the results of the last time we ran the demo. Let's take a look at the README file real quick. So what's going to happen here is when we run the simulations or the demo script here, it's going to do an MPI run with NP3 oscillator on the oscillator mini app. It's the -F is going to tell it, the mini app, to use this catalyst.xml. That's going to set up Catalyst and give it the Python script to create the pipelines and do the visualizations and extracts. And the oscillator's text configures the oscillator's mini app to place the oscillators at certain points, at the frequency of the sinusoids, and the strength of the damping. So with that, I will run the simulation script. And OK, so it starts up, and it says that it started. From there, I just want to go and maybe open a tab so I don't have to do anything. Module load, ParaView. So this is either a second terminal or a tab in the terminal. Load up the ParaView module, start up ParaView. Go back to that for a sec, switch back into the first tab so we can see what's going on there, if anything. Go up to the Catalyst menu and click on Connect, and just hit OK. Now, all of a sudden, it puts up this message that it says it's accepting from the Catalyst coprocessor on port 2222, and we've got our pipelines. So let's take a look at the slice. I just clicked on that little icon to transfer the data over, but now I have to make it visible to render it. And so the VM had resized itself to be a bad size. So I'm just resizing this so we can actually see. Everything again. OK, so what we're looking at here are some slices from sending data from the simulation, and then we're interacting with it. I can go up under the Catalyst, pause the simulation to stop it from executing. We see over here that the thing enters the paused state. While it's paused, I'm going to set a breakpoint. It's already at time step 1047. I'll set the breakpoint to be time step 1060, just for the heck of it. And now we see that there's a red dot indicating the breakpoint's set. I'm just going to continue the simulation. And so now we see that the thing changed into the triangle. Well, it happened really fast. It was running. The breakpoint got hit. And so now we're at this breakpoint again. Let's reset the color map. We'll hit continue, and we'll see the simulation starts running again. let's say we wanted to add a visualization. Well, we can actually transfer the original data over, make it visible, clear this out, and now we're looking at the original data. I'll add a, so this is cell data, so with cell-centered data, just in general, VTK and ParaView don't handle that so well. So what we have to do is convert with a cell data to point data filter. So I'm going to add that, and I'll hit apply to make that happen. Add an ISO surface. I'm going to just make this a little bit larger so I can see. We can see that as the simulation runs, the values are changing. I'm going to delete that, add a range, hit OK. Oh, ParaView seems to have crashed. I'm going to try and reconnect here. So I was able to reconnect. I'm going to go back, transfer this cell to point data over, make it visible. So this is essentially where I was when it just crashed. Notice that the simulation didn't crash, which is kind of nice. ParaView crashed, but the simulation survived. And I'm going to check this compute scalars and go down here, try to add an ISO surface. I'm going to add 10 values. OK. So I think we've hit a bug in ParaView here. I'll try this one more time before I give up, but I'm going to do something different so I don't hit that same bug.
Tomorrow we're going to use 5.5, and we could retry this
Yeah.
example with 5.5. That might fix.
That might fix things. If not, we can tell Andy, that there's a bug. So now I've just enabled this ISO surface. ISO surfacing. I can look at the block index. So there are 2 blocks. Go back to solid color. Let's look at this contour filter. What I really wanted to do was add a few and generate the values. Let's see what he's done. This has all been configured, so he has this all configured through the Python script. I can add the compute scalars, and now that should give me an array to color by up in when I see it in our data array is there. Unfortunately, I think what's happened is that the simulation has evolved to the point where there's no more contours. So let me go back down. One last thing before I quit this is I'm going to try yet again to add some values. Hit OK. So we've hit a bug here. We'll report it to Andy. ParaView is a great tool in general. You do hit some bugs from time to time. OK, so that was the Catalyst Live demo. I hope it gives you a feel for what you can do with Catalyst Live. We hit a bug. We'll report it and see if Andy Bauer the Catalyst guy at Kitware can see if he can reproduce it and fix it. Other than that, I think it's a useful tool. I really like the fact that it's configured. You can configure a Python script to control your visualizations. The live feature is great for checking in on your simulation. If you want more info about Catalyst, here are some links that you could use in the slide deck to get to the various sources of documentation. Now, ADIOS, we've already kind of covered this yesterday, so I'm going to skip through. The next demo is SENSEI with Python. So Python is very popular with numeric computing, makes your life so easy. SENSEI comes with Python bindings, and this demo is all about using SENSEI from Python. A little bit of info about SENSEI's Python bindings. SENSEI, is based on VTK, so all of the classes in SENSEI, the data adapter, specifically the analysis adapter, these are derived from VTK object. So these are reference-counted classes. VTK has its own Python bindings generator that Kitware has developed over many years. But in SENSEI, we're actually using Swig. The reason we're doing that is VTK's Python wrapper generator only wraps API that has VTK data object star or VTK classes, things that derive from VTK data object. If you have an API method that takes a standard string, VTK's Python wrapper just skips it. So for that reason, our API uses things like standard string and other classes that VTK doesn't know about, such as SENSEI data adapter. So VTK's Python wrapper cannot be used with SENSEI. For that reason, we're using Swig. Swig is this tool that parses your header files, takes a configuration file, and it spits out Python bindings. So it's really great tool if you're trying to wrap a C or C++ code in Python. And it understands modern C++, C++11, and it has enough flexibility that we can teach it to treat VTK wrapped Python in the way that VTK expects. So Swig can actually play nicely with VTK's Python objects. So in SENSEI 1, the wrappings for SENSEI look exactly like the C++ API. In SENSEI 2, that changed because our API started using pass by reference for some of the arguments. And in Python, there's no pass by reference. Everything is pass by value. So for that reason, the Python API has changed a little bit from the C++ API. So anytime in SENSEI 2 where you see a pass by reference in the C++, that's actually going to be returned in the Python API as the return value. And instead of an error code, which the C++ API in SENSEI 2 all returns error codes as an integer, instead of that in Python, if an error occurs, you're going to have to raise an exception. And that's more Pythonic. That's what Python expects one to do, is raise exceptions. So there is that difference in SENSEI 2 between the C++ and Python in terms of pass by reference. Just something to be aware of. For developers, such as somebody writing a new analysis adapter or a new data adapter, if you want that to show up inside of Python, if you're writing it in C++ and you want it to show up in Python, we have this vtk.i file, which tells Swig the commands to do the wrapping. And this vtk.i has some macros, some Swig macros that we made to simplify the process of getting a new data adapter or analysis wrapped. So the first one is vtk swig interop. And you pass this the name of your class. And you use the full qualification if there's a namespace. So you would, in the case of Sensei, it's Sensei : class name, because we have everything in a namespace. So what this thing does is it defines type maps so that VTK wrapped classes can be passed through the API. So the VTK swig interop, let's say you have a VTK class that you want to pass through your API. You have to use this to tell swig that this is a VTK class, and this should be treated as a VTK class. The second one is VTK derived. If you have a class that derives from a VTK data object or any VTK class, you use this macro. So the first one, again, is for VTK objects you want to pass through your API. The second one is you're deriving a new class derived from a VTK object. This includes the Sensei classes because they are all derived from VTK objects. So what the second one does is enables the memory management for VTK's reference counting system to work with swig. So swig will create instances of your new class. The second macro VTK derived tells swig how to free those up, and so there's no memory leaks. With these things, you can safely pass a VTK class into Sensei, but this doesn't do anything about VTK itself. VTK will not understand how to consume Sensei classes, even though they're VTK objects, and one would expect that VTK would understand how to deal with its own objects. Because of the different wrapping systems, that's just not possible. So integrating Sensei into a simulation written in Python, the steps for doing this, first of all, you have to compile VTK with Python enabled. This is not on by default. Python comes often as a part of various backends like Catalyst and Libsim. Libsim compiles its own version of Python. So it's important that the environment be configured correctly for this, and that these backends are actually compiled with Python enabled. Second step is when you're building Sensei, you've got to enable the Python features. Those are off by default. The third thing is the analysis and data adapters. You can write your own and wrap them. You could use the VTK data adapter, which in Python we've seen yesterday. We went through a bunch of Python scripts to create VTK data objects. So the VTK data adapter is really easy to use. In Sensei 2, we actually added a Python data adapter where one can have a pure Python data adapter. And I'm going to show an example of that. The fourth step is to instrument your simulation with the bridge code to set up the data analysis adapter and then invoke them as the simulation runs. And then the last step is to create the runtime configurations, like the XML files, the Python Catalyst scripts, visit session files, and so on. So this demo includes, or is this Newton mini app. Newton is an n-body gravitational simulation. It's a single file with less than 400 lines of code, so it's very minimal. So I wanted to write it that way so that it would be easy to follow what's going on and see where all the Sensei stuff is. It solves Newton's law of gravitation using this velocity varlet, which is the absolute simplest way that you can get an accurate solution for this problem. It's a direct solver, so it's kind of like a brute force method. It's order n squared. It doesn't scale very well. Every particle in the simulation is influenced by every other particle. So there are much more efficient ways to do these things than I've done it, but my goal was simplicity. I just, out of curiosity, I took a look at this n-body 6, which is this high-quality production gravitational simulation for n-body, and it was about 6,000 lines of code. I didn't want to do something like that. for the mini app because that would be very confusing. So when you run the mini app, you get something like this. We've just got a massive object in the center of the simulation, and we're just randomly putting in a bunch of like planetoids and setting them off with a little bit of a nudge. And as things evolve, these things spin around and interact, and some come close to the large object in the center and get flung out, just so we can see things moving. So instrumenting the simulation. So here's the main, our Python main for the simulation. I've just omitted the command line parsing because the thing's configured from the command line options. The basic steps that are happening in the program is that you parse the command line, you figure out how many bodies and ranks, the initial conditions. It creates this uniform random IC, which just creates this large mass in the center and then scatters random particles throughout this domain that you just define. We're going to allocate all of the NumPy arrays, these IDs, XYZ, M, Vx, Vy, Vz, Fx, Fy, Fz. So this is the forces, velocities, mass, position, and ID of all the particles. So that's our entire simulation state. Set the time step, and then we're just going to loop and use the velocity verlet method to update the particle positions. When we instrument it, we add in the bridge code. So this creates a Python class, which I've defined. We'll take a look at that in a second. We're going to initialize our bridge. We're going to tell it to update. This will let us process the initial condition. And then after we do our velocity verlet, we're going to do an update. So every time the new simulation solution comes up, we're going to tell, give a chance to push through SENSEI. And then finally, at the end, we're going to finalize. So let's see, I've added 1, 2, 3, 4, 5 lines of code to instrument my simulation. So not too bad. So here's the analysis adapter class. That's my bridge code. Again, the pattern here is that the bridge code manages the data adapter and the analysis adapter, and it pushes data through SENSEI to the backends periodically. So this is exactly what this class does. We'll take a quick look at each of the methods. But you can see here the finalize, really simple. If the analysis is a post hoc, this one's for I/O, it calls finalize. Otherwise, it does nothing. In its constructor, it creates a new VTK data adapter. So this example uses the VTK data adapter. And it creates a placeholder for the analysis adapter. But it sets it to none because it's going to be configured from the runtime conditions. And then in the update method, this is where it's going to try and push data through SENSEI if it needs to. So let's delve into these functions a little bit. So in our bridge initialize method, I'm taking a bunch of command line arguments here and the name of an analysis, or the name of an analysis adapter. And so I'm just saying, OK, if the analysis adapter is libsim, named libsim, let's create one of those. So this basically, this if-else statement lets me test out the Python bindings for these various analysis adapters. So here, we're doing a libsim analysis. If it's Catalyst, we're doing a Catalyst. If it's post hoc, we're using VTK.io. This will let us dump VTK files for visualization or configuration of the Catalyst Python scripts. Or I can use the SENSEI configurable analysis. This one is the one that takes the XML file. So in general, I would say that these ones I added to test the Python bindings, and probably a user wouldn't want that. They'd probably just want this one. So finally, there's just some error checking. And with that, our analysis adapter is configured. So second method we're going to delve into here in this deep dive is the update. So this is our bridge code. The update method gets called every time the simulation solution state changes. And we're going to see if we can push data through SENSEI into one of the backends. So what we do, we're past our new simulation state in these NumPy arrays, the IDs, positions, mass, velocities, and forces. We're going to take these arrays and we're going to make a poly data set, a VTK poly data set out of that. We'll look into this function in a second. To get this through the SENSEI API, we're going to convert to a VTK multi-block data set. We're going to set the number of blocks to the number of ranks. So each rank has one block. And we're going to set the block on our rank to this poly data set that we just created. So poly data set is a type of unstructured mesh, but it's limited into what type of cells you can have. So this is one of the quirks of VTK. Poly data is optimized for rendering versus unstructured mesh is a little bit heavier weight and doesn't render as fast. So poly data is essentially an unstructured mesh. You can have points, triangles, lines, and strips. So for this simulation, all I have are these bodies that have these positions. So I'm using the poly data as points. Once the data adapter, so once this multi-block is set up, I have my data adapter as a VTK data adapter that comes with SENSEI. All I'm going to do is pass in the multi-block and set the time step info. So this is an example of where if you can create a VTK object and you know what data you're going to send and you're OK with sending it all, you can use this data adapter to make it really simple. You don't have to do a lot of coding. In fact, I didn't do any coding. All I did was construct this VTK object, and I passed it in. Then, of course, my analysis adapter, I'm going to call execute and pass in the data adapter. Whatever that analysis is, whether it's Libsim, Catalyst, whatever, it's going to take the data adapter and use it to get the data and do its thing, finally releasing the data out of the data adapter after everything is done. And so that's my update function in my bridge. Taking a deep dive down to another level, this points to poly data function that creates my VTK data set for my multi-block piece on this rank. Again, I've got the simulation state being passed in. I've got this function that converts XYZ arrays to VTK points. We'll go down into that in a second. I'm creating the cells. Here, this is a cell array. Similar, it's a little bit simpler than the unstructured mesh. We can take a look at that. I'm creating a scalar here from the IDs. So these are the particle IDs. They're unique across the whole job. Mass is transferred. I have this function 2VTK vector. By the way, these 2 VTK points, 2 VTK SLs, these are all functions I wrote, and we'll look at them on the next slide. Basically, this takes these 3 arrays and creates a vector and the vector magnitude. I create a poly data. I pass in the points, and then I pass in all of these arrays as point data sets. And I set the vertices to cells. Remember, poly data can only represent points, triangles, lines, and strips. So verts is the way to represent points. And then I return that object. So in this example, these functions all create a deep copy. But that's because this was written before the AOS SOA thing was completed. So it could be updated to be 0 copy. And I put that as a note here that I need to get to test out the new 0 copy stuff. DG is David Goby. He's the one that does the Python bindings for VTK. He actually doesn't work at Kitware. He's a professor up in Vancouver, British Columbia, Canada. And he's made the zero copy with the SOA pattern work from Python, which is wonderful. So we can do the zero copy stuff from Python as well. So 2 VTK points. Here's my function to convert the XYZ arrays into points. XYZ is going to be an empty NumPy array at first. I'm telling it to use float 32, 3 times the length. And then these colon statements are just Python magic to copy to every third element. The first one starts at 0 and then goes every third. The second one starts at 1, goes every third. And the third one starts at 2 and goes every third. So I'm just basically interleaving these 3 arrays. It's beautiful how NumPy can do these things. This is a really key one if you're using VTK. I know Jean showed yesterday some ways of doing these conversions. He's actually using the newest stuff. So if you look at the examples he did yesterday, the wrap data set, I think you'll find in his examples, that's very new. This is kind of the older way. I'm not as familiar with the newest developments in VTK. VTK has this library, and I've imported it as VTK-MP. And it has these helper functions to convert from NumPy into a VTK data array. So the return of this NumPy to VTK, again, this function is provided by Kitware with VTK itself. The return of it is a VTK data array. So this is something the VTK can work with. I passed in my NumPy array, and I told it to make a deep copy. You could set that parameter to 0, and it will do a 0 copy. There are also some optional arguments that tell VTK how to deal with it, if it owns it or you own it. Again, I just did deep copy because I haven't had time to test out the latest stuff. I tell VTK it's 3 components, and this is the length, nx. And I create a new points object, and I pass that VTK array into the points object as the data, return it, then I can stuff it into my polydata. With cells, again, VTK polydata only supports points, triangles, strips, and lines. So here we have points. So this is an example of how to make point cells for polydata. I start out with an empty array 2 times the length of my number of bodies, number of particles. The reason that it's 2 is because the VTK cell array has a length of the cell and then the number of indices for each cell. With a point, you only need 1 index to describe a point. So I've got those 2 values. I've got the length of the cell, which is 1, and then the index into the point array for the second value. So you'll see, if you were to dump this array, you'd see something like 1, and then an index, and another 1, and then another index. So every other number would be 1, and then every other number would be a point index, or the index into the points array. And so that's what this does, is it takes every other value in the array, and it starting at 0, sets it to 1. And then every second value, starting at 1, I just generate a 1 through n in 32 array. That sequence of values. So increasing sequence of values. I create the VTK container for cell array, and I pass these in using this conversion to convert a NumPy into a VTK data array. And I tell that conversion to use a VTK ID type. That's what VTK expects. So this is another argument to this NumPy to VTK helper function that VTK provides. You can tell it what type to use. And that's useful because VTK ID type is a compile time thing. You don't know actually the size of it. It's an integer type, but you don't know the size of it. It could be a 32-bit, it could be a 64-bit. That's a compile time thing. So it's safe. This is probably the safest way here to ensure that I get the right size integer for VTK IDs. Now, that was the cells and the points, so my topology and geometry for my data set. And now to pass in the scalars, I'm doing the same thing again, just using this helper function VTK provides. You always have to set a name with these arrays that go into point and cell data in VTK. It will crash if you don't. So I set the name. And for vectors, do the same thing again. Here I'm making a deep copy. With the new SOA stuff, we could actually do zero copy here, interleaving these values, using the conversion function, setting the name. There's a typo here. This would actually have the name, inserted. There'd be like a %s, and I'd be inserting that name in. So there's a typo in that. So it would look something like this, but it would be v%s name, similar to how I'm doing it down here. So anyways, and then I compute the magnitude of the vector. The reason I'm doing that is because I can visualize that, whereas with the vector field itself, I'd have to glyph or do some other kind of visualization. With the magnitude, I can actually just color by that. So this is a convenient way to make an array to color by. And now I return those. And so that's really the entirety of the code, the SENSEI code for this simulation. This simulation is packaged with SENSEI, so it's in the source repo. All of the code, the data adapter, everything, the whole thing, soup to nuts, is in there. It's also in the SC17 demos folder. We'll go in there in a second and do the runs, but I copied over the Python script into there, so the demos folder there is completely self-contained. So the one thing I want to do, and this is the part about SENSEI that I'm the most excited about, is this in-transit part, where you can take these different backends, the Catalyst, the Libsim, you can run them in situ directly, or you can use it, ADIOS, to send the data over the network and move it to a different set of nodes. And SENSEI allows you to do this just by changing the XML in the configuration file. So you get all of these configurations. You can switch in between Libsim and Catalyst, or you could do in transit, sending data over the network to another set of nodes using Libsim or Catalyst. All of these configurations are really easily achieved just by modifying XML code. So what we're going to do is we're going to have two jobs. In the first job, it's going to be our Newton Mini app, the simulation. I'm using the VTK data adapter. This is code that comes with SENSEI. What you do is every time you want to pass data through it, you just pass it a VTK object that you create. So when you use the VTK data adapter, all you have to do, you don't have to do any coding for that. All you have to do is create the VTK object and pass it in. So there's no SENSEI-related coding. I'll use a configurable analysis adapter in this example, so I can have an XML. That XML for this will configure ADIOS to write over the network. In my second job, the ADIOS endpoint is a binary main program that comes with SENSEI, and it's compiled with SENSEI. It's a simple main program. All it does is it creates an ADIOS data adapter that receives data over the network or from a file. I mean, that's the nice thing about ADIOS. I can change the transport. I could be writing to HDF5, reading from HDF5, or I could be writing to FlexPath and reading from FlexPath. It's going to take an XML file and create a configurable analysis adapter for the back end. And XML is going to choose, I'm going to choose one of these out of the using the XML file, either Catalyst or Libsim. And so here I've showed the XML that comes with the demo, and I have different XML files here rather than putting it all in one. So these, if you want to use Catalyst, there's a XML file for Catalyst that just basically says, okay, start Catalyst, give it this Python script. The ADIOS configuration for the in-transit, I'm going to choose FlexPath. The MPI will send it to disk if you want to try that. Data spaces, it's currently incompatible with data spaces. There's some quirks with that. Data spaces, by the way, is similar to FlexPath. It transports things over networks. If I wanted to use Libsim, I'd give it this file. So what am I doing in here? I'm telling Libsim to do a pseudo-color, telling it the plot variable, the IDs, telling it where to write, so on and so forth. The last one is a histogram analysis. This is a toy that comes with SENSEI. OK, so running the demo, we'll switch into the VM, and we can try this. So there are two terminals. We're going to use two terminals, and we're going to have two jobs in all cases. So this will be an in-transit demo. So the simulation is going to be the same for every use case. We're going to tell the simulation to run 100 iterations, and it's going to configure itself to use ADIOS transport. Now, these are three different cases. We'll run three different ways. In a second terminal, these scripts start up the ADIOS endpoint and tell it to use either Catalyst or Libsim or the histogram with this XML file. Yeah, we'll be done. We'll be done shortly. So switching over to the VM, I will just make the font a little bit bigger. I'm going to change into the demo directory. Go into the Python demo. And I've got a clean script in there. I'll just run that. That just cleans out any cruft from the previous run. I've got a bunch of different scripts in here that are used to run in various configurations. Let's just take a look at one of those. So Newton ADIOS in transit. It's going to load the SENSEI module. It's going to start the simulation with 4 ranks. So Python, Newton.py. This is the mini app, Newton.py. It's in the same folder. I'm going to tell it to use the configurable analysis, and I'm going to pass in this ADIOS config XML. That is the one that we just looked at that configures ADIOS for FlexPath, and I'm going to tell it to how many iterations to run. So with that, I'm going to start up Newton ADIOS in transit in the shell and tell it to, I don't know, do 20 time steps. Okay, so this started up. It configured to use FlexPath. FlexPath is going to wait because of this buffering. It's going to wait for the other end to connect. And I'll open a new terminal. And now in my second terminal, I'm going to CD into the demo again. Now this time this is the second job that's going to receive the data from the first job, and I'm going to configure it to use Libsim. So in this terminal, I'm just going to run the Newton Libsim script. Let's just take a look at this script before we run it, just so we're aware of what's going on. OK, so in this script, I'm going to load the SENSEI Libsim module. So this is important. You've got to load the right module for the backend you want. The backends, again, are incompatible with each other. They use different versions of Python and different versions of BTK and various dependencies. So they each have their own modules. We're going to use MPI exec. Oh, wait a sec. This is in situ. This isn't in transit. OK. Okay, sorry about that. I had the wrong script loaded. So again, loading the SENSEI module. This is the in-transit. So on the receiving side, we have the ADIOS analysis endpoint. This is the standalone program that ships with SENSEI that receives data from ADIOS. This thing takes an XML file. This is passed with the -f argument and uses this file to configure a SENSEI configurable analysis adapter. In this XML file, I'm telling SENSEI to use Libsim. I'm telling the ADIOS analysis endpoint to use FlexPath, and that this is the file to get the connection info from. So now when I run this, you'll see this will start up. The first terminal, you can see periods coming out, and it writes a period for every time step. Okay, so it computed the solutions and sent all the data through FlexPath. Now, the simulation solutions are small enough in this instance that FlexPath can buffer these. So the simulation had already completed while the visualization was running. The visualization took a lot longer than the simulation, and the nice thing about that was FlexPath buffered that and allowed that to finish way before the visualization finished. So let's see. Now, after that run, I have 20 new images. Let's just take a quick look at one of them. Let's look at the 20th. And I've got, basically points for all the bodies. If I were to animate these, you'd start to see these moving. I'm just going to call that good for the sake of time. Now let's run it with Catalyst. Let's do the clean to clean out those image files, so we now no longer have any images. Let's now run this again with Catalyst. So the simulation side does the same thing. We're going to configure it to run with ADIOS for 20 steps. So executing that in the first terminal, that's going to start the simulation up. It's going to start sending data through FlexPath, but FlexPath is going to say, oh, wait a minute, I don't have anybody to receive. I configured FlexPath to work in this blocking mode. So I'm going to start on terminal 2, catalyst in transit.sh. Let's dump that file really quick, just to make sure we know what's going on in there. This is basically the same thing that I did with Libsim. I'm starting up the ADIOS analysis endpoint with 4, telling it FlexPath. The only thing I'm changing is I'm passing in a different XML. So this is going to set up Catalyst. And we've already pre-generated this Python script using a representative data set. And so this is going to start up Catalyst. And you'll see data start to move, windows pop up. The window is kind of Catalyst rendering window. Although I think in ParaView 5, they've actually made it so that you don't see the pop-up windows anymore, which is nice. And so we're going to go up to time step 20, and then we'll be done. And so now we have a bunch of images. Let's take a look what we got. And so here's what it looks like with Catalyst. I've rendered the points and glyphed them with spheres and scaled them by some value, by the mass. And so there you go. So what I've just demonstrated is I've done the in situ, I've done the in transit configurations. I've run the simulation in parallel in one job. And I've shown how to use SENSEI to switch very quickly in between Libsim and Catalyst without any code changes, simply by changing the XML. Now, very quickly, I'll clean out these files so there's nothing in there. Now, that was all the in transit. So the simulation was running, sending data over the network to a second job using FlexPath. You can do this just as easily in situ without FlexPath. For that, I've got this Newton, these Newton, let's just run Catalyst and we'll call it good. I've got the script here to start this up, this Newton Catalyst startup script. I'm, again, using MPI 4 ranks to start up the Newton Mini app. I'm telling it to use SENSEI configurable analysis, and I'm passing in the config file for Catalyst. This is the same config file I just passed into the ADIOS endpoint in the last run. But let's do this one and see what happens. Oh, right. So I have to give it time steps. You're right. Thank you. Okay, so it's starting up. It started Catalyst. It's doing this in situ now. At every time the simulation updates its state, it renders to Catalyst. And we've got our images. Now, I'm going to skip this because we're running out of time on this. But there's a Newton Libsim in situ script that will redo the example with Libsim and run it in situ. So I think this is the part that I'm very excited about SENSEI, that it allows you to switch in between these back ends, do in transit, in situ, really simply once you have it all set up. And with that, I'm going to ask if there are any questions, and I think we adjourn for lunch. Well, in that case, let's go to lunch.